Okay. Hello and welcome. Today I'm going to be giving a presentation on the applications of linear algebra in machine learning and deep learning. So we'll be covering three topics roughly: gradient descent, linear regression, and neural networks as transformations of a vector space. First of all, what is gradient descent? Gradient descent is an algorithm that is used whenever we want to optimize a function that is parameterized by some parameters theta, right? And we want to optimize it in the sense we want to find the minima of the function, right? And this is an algorithm that is devised that we can use to iteratively update our estimate of theta and try to find our optimal parameters. Okay, so one we generally have a function that we want to minimize, right? In this case, we have our loss function g of theta. This is a common function you'll see. This is the mean square error function. This is the mean square error. Right? It's a metric that's you and over here. Okay, let's break this expression down. We have h of x and then we have y, right? So h is our model. It is what we it is the function that we want to represent, and h of x we want it to be as close as possible to y, right? Y and what we see the summation notation. Basically, if we have m input points, then we're gonna sum the over this difference squared over all of the input points, and we're gonna take that average. So we divide by m, and you see this half factor. This is just for clean math, as we'll see later. And so what we do is we want to find the optimal set of parameters, the optimal vector theta, right? Theta can have multiple components. We want to find the optimal vector theta such that this cost function, this j, is minimized. And what gradient descent tells us is to follow this updation, this iteration rule, where we take where our next theta, our new theta is going to equal theta minus alpha times the gradient of j with respect to theta. What the gradient of j with respect to theta represents is, okay, suppose we have theta is a 2D vector, has two dimensions, and this is our space, and we you can imagine along this z-axis, pointing towards you, that there's our loss function, that is a j of theta. So what gradient of j of theta tells us is that at any given point, what is the direction of steepest ascent? That is, if I nudge my theta very slightly, what is going to be my increase in j? So if we take suppose j of theta, if we look at this point, we look at the gradient, right? What it this is this graph, by the way, is of minus of grade j of theta, and you can see that this is a vector field because we have two axes, right? So if we take a point over here and we find the gradient, the length of the vector or the color of the vector represents the length of the gradient of j of theta, and the direction represents the direction, of course. And what this rule tells us is that if we start at some initial estimate of theta, then what we're supposed to do is we're going to follow along the gradient. We're going to follow along this vector. We're going to move a certain distance that is given by alpha, and then we're going to stop. Then we're going to compute the gradient again, and we're going to move again. So even though initially we might, and what we're hoping to do is we're trying to do this iteratively until we come at a point where our theta stops changing. And when theta stops changing, that means that we have reached some sort of an endpoint, some sort of a minimum, right? So suppose we start over here, right? Suppose we start over here, even though initially we're not pointing towards the global minima. Also, if you notice, all of these tracks they point towards they end up going at one point which is this. And at this point, if you calculate gradient of j of theta, then you that will come out to be zero. So even though initially we are not moving towards the minima, because the gradient of j of theta gives an estimate of how j behaves locally. So the slope will be in this direction, and if we continue following this path again and again, we'll end up coming here. And over here, our gradient of j of theta will become 0, and we will reach a minimum. All right. and visualize in 3D space, this is what it'll look like. We start from this point, and if we continuously iterate, make very, very small iterations, small updations, then we reach the global minimum over here, where our j of theta is 0. What this means is that slight nudge in the x-axis, in our x, in this case, x is theta 1, y is theta 2. Slight nudge in theta 1 gives no change, gives roughly no change in j, and slight nudge in theta 2 gives no change in j. So now our next topic, which is linear regression. So linear regression is a special optimization case where the model that we use, like in the last slide, we saw h of theta, right? Where the model that we use is linear. So in this case, we have an input vector which is x1 and input features, right, which are called x1, x2, x3. This can be anything. It can be suppose you try to predict the maybe the price of the stock market for tomorrow. So in this case, we use and you're using a linear model. This is a terrible model by the way, for stock predictions. But suppose x1 could be the price of the market yesterday, x2 could be the price of the market the day before, and so on, so on, so on. And you're trying to fit a linear model to predict the price of the market tomorrow. And this is this basic case. This is the case where you have only one input feature, but in general case, what would look like this: y equals theta. This is the function you're trying to fit. You're trying to find the optimal theta, right? So a general case would look like this: theta naught plus theta 1 x1 plus theta 2 x2 plus theta 3 x3, so on, so on, so on. And what we're trying to find using linear regression is the optimal theta 1 and theta 1 theta naught that minimizes our function, our MSE function that we saw earlier, right? That is the mean squared error. If you look at it's in vector form, it looks like this. If you look at this closely, this is the dot product, the inner product of a vector with itself, which is the norm of the vector squared, right? So we have x theta minus y. X theta. Okay, so first of all, what is x? X is is a matrix that is characterized by this, characterized as such. Each of the input vectors, each of the vectors of x, the row vectors, represents a particular point in our data set, right? So we have for one point we have an x1, x2, x3, x4 that will represent one row. Maybe we have another point, right, and another point in time in our stock market that gives us another x1, x2, x3, right, and so on, so on, so on. So once we stack up all of these row vectors, we get our final matrix, which is x, right? And this x is a matrix transformation, which, when acted upon theta, gives us our prediction that is 1, right? It's a prediction y. It may not necessarily be equal to our true y. And what we're trying to do is we're trying to find this prediction. X times theta gives us a prediction. We subtract y, and then we take the norm of that. So what we're trying to do is we're trying to minimize this j of theta, which I'm trying to minimize. Right? So we're trying to minimize the difference in between a prediction and our original and our true value squared. And again, we take 1 by 2 m because m is the number of samples in our set. And to minimize this, now we're gonna expand this out, right? And we get this expression: theta transpose x theta minus 2 theta transpose x transpose y plus y transpose y, and 1 by 2. This is a constant factor, right? We can and now what we want to do is we want to find the optimal theta such that this the gradient of our cost function equals 0. So for this we use matrix calculus. Matrix calculus is nothing but a set of rules. Uh, performing differentiating scalar values is relatively simple, but when you have matrices and vectors in the question, differentiating those can be slightly tricky, right? And what does that even mean? So matrix calculus gives us a set of rules that allows us to differentiate. So when we have in all of these examples, we have x is a vector. These are the four basic rules. X is a vector and A is a matrix. So when we have a matrix times a vector, a matrix acting upon a vector, we get a resulting vector, and we're differentiating it with respect to another vector. What we're computing here is essentially uh, if the numerator vector, right, we take the first element of the numerator vector and the first element of the denominator, and we differentiating these the top with respect to the bottom. Then we do the second. We take the second element of the numerator and we differentiate it with respect to the first element of the denominator, and then we put this in this as a second entry, and we do this for the entirety of the vector of the numerator vector. Then we do this again, right? We take second element of the denominator and we differentiate it with respect to the first element. We take the first element of the numerator and we differentiate it with respect to the first element of the denominator. and we continue this, and we form a stack of rows. So it's just a neat way of representing normal, what do you say, differentiation, right? But on a larger scale, and we get a resulting matrix because we're differentiating one vector with respect to another vector. So we have n cross n permutations, right? And similarly, you can imagine the second expression, right? And the third expression, right? This is the dot product of a vector with itself. Okay, this is very simple. So suppose our input vector is x naught, x1, x2, x3, right? And when we take dot product with itself, we get x naught squared plus x2 squared plus x3 squared. And you're differentiating this scalar quantity with respect to the vector, right? X naught, x1, x2, x3. So what you do is first you take this scalar quantity, differentiate with respect to x naught, you get 2x naught. Then you differentiate it with respect to x1, you get 2x, and so on and so on. And you write this as 2 times x, which is our input vector, right? Which is what you see over here. And you can also the fourth expression is a bit complicated, but you can derive this as well by expansion. Okay, so first we need to find the point where the gradient equals zero, as we saw earlier, right? So we differentiate our j with respect to theta. And for this expression, we see this corresponds to the, in this case, our theta is a vector, right? So this corresponds to the fourth rule. So if we take theta transpose x theta, we differentiating this, upon differentiating, we get these two quantities, x transpose x theta plus x transpose x theta, right? And then we take the second quantity minus 2 theta transpose x transpose y. And you see that this expression, x transpose y, is nothing but a vector, right? And mind you, if x is works for a matrix, you can also treat x as a vector, and the resulting rule would still be valid. So we have our input vector times another vector slash matrix. So we can use the excuse me. So we can use the second rule because theta is transpose over here, and we get a, which is directly this expression, and we can just place it here. So minus 2 times x transpose y. And then the third term is not dependent on theta at all. So the differentiation leads to zero, right? The gradient becomes zero. And now when we combine terms, and then we get this expression, right? 2x transpose x theta minus 2x transpose y equals zero. And when we solve for y, we get theta equals x transpose x minus 1 and x transpose y. And this actually looks really similar to the pseudo inverse formula, right? Anyway, so one thing I'd like to touch upon is the difference between PC and regression. This is something that confused me quite a bit as well, right? But the key difference is in PCA, we try to as we learned in class, we try to minimize the sum of the squared distances from the hypotenuse, right? The projection. Whereas in linear regression, we just try to minimize the difference between our prediction, not the distance from the projection, but just the vertical distance. All right. So the way this is different, and regression also has some advantages over PCA. And these two optimizations, they you might think that they're the same, but they do lead to similar results, right? Like the estimated line of best fit from regression and PCA could look very similar, but mathematically they're different, right? Numerically they're different because we're performing different optimization problems. So one disadvantage of PCA is PCA, technically numerically you can apply it to any sort of data, but what we're trying to minimize over here, we have to take a close look. We have x1 squared plus x2 squared, but like along each axis, right? And the problem is, suppose my input data is maybe it's the I'm trying to predict the weather for tomorrow, given I'm trying to find the temperature for tomorrow, given the humidity level today and the temperature today, right? So the problem with this is when I'm taking the humidity cut difference, I would and or the and I'm squaring that. I'm taking the temperature difference and I'm squaring that. Technically, like by physics, these two quantities have different dimensions, and they cannot or they should not be added. Even though you can numerically add them, they should not be added because that the resulting quantity has no physical meaning. So, what our optimization problem, like we're trying to minimize the sum of squares, but the sum of squares has no physical meaning as such. So, unless my input feature has the same unit for each dimension, right? It is not ideal, or it's not correct. Technically speaking, it's not correct to use PCA. Whereas in linear regression, we just calculate the difference of a prediction minus difference of a prediction and the true value. So we just squaring the predicted temperature for tomorrow and the true temperature for tomorrow, and we're adding that up, and we're adding that across all points. And the units for this all match up. Another thing is, if you perform linear regression, it's invariant to scaling. What I mean by that is, if I take any axis, right? If I take my data and I stretch it along one axis, suppose I stretch it along the x-axis, and then I perform PCA, and then I take the resulting line, I take my resulting data, and I stretch it back, right? The resulting the line of best fit that I obtain will be the exact same as if I had never performed the stretching in the first place. But in the case of PCA, if I stretch my data along one axis and then I perform PCA and then I stretch it back, the resulting line will not be the same as if I had never stretched it. Right? This again is because we're adding the error term. It depends on the scale of each axis. Right? Okay. Now we're going to touch about neural networks. Neural networks, they're the core of DL, and the core of neural networks is linear algebra, right? It's because neural networks are nothing but a bunch of linear transformations. The problem with in today is that many people view uh, neural networks as black box functions, right? But if we use linear algebra, if we use them as linear transformations, then it allows us to demystify their inner workings. Right? So what are neural networks, first of all? So neural networks are nothing but they're trying to make predictions on a certain input value x, something similar to linear regression. So we have an input vector, right? X. And what neural networks do is neural networks transforms this input vector into our prediction into another vector, and then does this consecutively again and again, right? So we have a four-dimensional vector, and we apply linear transformation, and we get a 6D vector. Then we apply another linear transformation, we get another 6D vector, then we get a 3D vector. And what you can imagine, like each transformation, visualizing this in higher dimensions is pretty difficult. So if we imagine a 2D transformation, right? We have this input vector x, right? That is a 2D vector. And up after transformation, you can see this is how it's transforming the space. I'm sorry. Uh, yes. And one problem you see with this is, if I multiply the input vector with the matrix W1, then W2, then W3, the problem that comes is how is you can just combine these transformations into one transformation, right? W1 times W2, then the times W3, then I can just apply this operation on the input vector. So to deal with this problem, right, what we do is after application of one what do you say of one layer, right? These are called a bunch. Each of these is called a neuron, and a collection of neurons vertically is called a layer. So after application of a layer, after application of a linear transformation, we apply something that's called an activation function. What an activation function does is it's some sort of linear transformation that allows us to increase our representational power. Right? One linear transformation is called the tanh, right? Tanh is a monotonically increasing graph that squashes all of its inputs between -1 to 1. Another very common and popular activation function is called ReLU. That stands for rectified linear unit. What this does is, if we have an input vector, right? What it does is, if each of the for each component, if the component is greater than 0, it keeps it as it is. But the component has a negative value, it it truncates it and it gets it to 0, right? And this performs really well in practice. So over here we're visualizing our input a transformation, right? So first we have also one detail I skipped over is we also add a bias term, which is basically after our transformation, we want to perform some sort of a shifting to increase our representational power. Even though like neural networks could work perfectly fine without biases, but we generally use this, that after transformation we add an offset. So first we perform a transformation, right? And then we add this offset, and then we apply a activation function, which is a tangent in this case. And you see the grid lines. This is what causes a non-linearity, right? It squashes this is our entire input space. And we do this recursively, right? Then we have a new space. Again, we transform it again in the next layer, and then we translate it, and again we apply the activation. So this is our problem, right? Suppose we have a problem, and we want to these this is our input vector, right? Our input vector has two dimensions, x1 and x2, x and y, suppose, and we have two sets of data. The one is the blue points. One set of data lies on the blue points, one set of data lies on the red points, and we want to develop a classifier, a linear classifier that can distinguish these two, right? But if you see, there is no linear boundary that can very clearly, cleanly, and neatly distinguish, differentiate these two boundaries, right? This is the best we can do, but you see there's some sort of overlap. So what we need over here is a non-linear transformation. And we perform this nonlinear transformation after applying a linear transformation using a matrix. So we apply a 2 by 2 matrix on this, and then we apply our tanh function, and we get this new warped space. And you can see how the lines change. And now what we do is, now you can see that there exists a clear linear decision boundary that can separate our two regions. So this is the power of neural networks, right? It has a great representational power, and it adds more complexity to our model. Okay, here is a visualization of a neural network that's under training. And what you can see over here is, this is the input neuron. This is our input vector x1 comma x2, and this is the scalar function that scale this is the vector that our input is being mapped on, right? And you can see, since at the first step, and the activation function we're using over here is the rectified linear unit, ReLU. So you can see at the first step, what we're doing is we just applying the transformation, then we apply the activation function later. So since we just apply the linear transformation, you can see that the activation, the resulting vector is also just linear. But once we apply the activation function on top of the ReLU, and then we perform another linear operation, another matrix multiplication, you can see that the output is no longer linear. And you can see try to find this decision boundary. Suppose we had no activation function. What would happen was, this would be linear. Then our next layer would also have linear outputs. Then our final decision boundary would also be linear. And it would be impossible to classify these points using a linear decision boundary. And we train neural networks using gradient descent, as seen as in the first topic, right? You can see it learns a very neat and nice representation. Okay. That's it. Thank you. So what we saw today was how we can use linear algebra to solve uh, to visualize neural network transformations, and how we can perform gradient descent, and how can we visualize it using vector spaces. And then we touched upon linear regression, right? Which is a classical algorithm that is used to make predictions. Okay. Thank you so much.